Welcome everybody in the lecture hall in Zoom from the future. Today we are going to finish the lecture on white column stores with the example of HBase, and then we'll proceed to data models, in particular for the normalized data, nested, heterogeneous, and data frames. So before I continue with HBase, I wanted to first remind you of the model that we have. It's very similar to a relational model, but there are a couple of differences. The first one is that the primary key can only be one column called the row ID. The row ID is sorted. The second difference is that the columns are organized in column families, right? So we have column families here with colors, and then the actual columns within the column families. So that's the second difference. Columns can be added on the fly, totally on complete search, and the column families, it's a bit heavier. So this is also in contrast to relational databases, where adding a column to a table is not something that is lightweight. Another difference is that there are no types whatsoever. Integer, string, date, nothing like that in HBase. In fact, everything to HBase is just zeros and ones. It's just data. And whatever you want to do on top with types is done one level above in a programming language where you actually put the data in there, but HBase doesn't know anything about data types. The second thing that we saw then after the logical level is the physical level. And at the physical level, we saw that, as always, we partition the data because otherwise it would not fit on a single machine. And the way we partition the data in a white column store is both horizontal and vertical. We partition horizontally in so-called regions that are just intervals of row IDs with min inclusive and max exclusive. And we also partition vertically by column family. So what we call a store, the level of storage, is the intersection of a region, interval of row IDs, and a column family. Next, the assignment of the stores to the region servers is done regions by regions, meaning that a region server will always be responsible for all the stores within the same region, right? But they are still stored separately. Then we zoomed in and we saw that at the level of a single store, so column family and interval of row ID region, we saw that we store cell by cell, and every cell is actually a key value physically, where the key is the row ID, the column family name, the column name, and the version. And then, of course, comes the value of the cell. And so the way that a cell is stored on disk, as we saw, it's just a flat list of cells that are sorted lexicographically by key values, right? And we looked into the binary formats with how this is all done with zeros and ones. But basically, what is stored is just a flat list of cells. Then we saw that the name that is given to the actual files that contain these lists of cells, that's called an HFile, and this is an HDFS file. It's stored on HDFS as a file. But we saw that it's not just a dump of the flat list of key values, because otherwise it would be too long in order to find key values in there. So there is a bit more than just the flat list. There is also some index. And in order to build the index, we organize this flat list in blocks, but this has nothing to do with HDFS blocks. This is why I call them H blocks here for HBase. It's roughly 64 kilobytes, more if the last value is bigger than that. And now that we have the H blocks, we can build an index on these H blocks, which makes it very easy to retrieve the cells, because then given a key, you look up in the index which H block you're supposed to read from, and then you read the H block, okay? Okay, so this is the hierarchy that you have tables made of regions, made of stores, made of H files physically, made of H blocks, made of key values, and a key value corresponds to a cell. For whom is that clear? This we already covered, right? All right, good. Then we saw that the challenge was that we cannot random access HDFS, so we cannot just insert data so easily because the files need to be sorted at all times. So if we insert a key value in the middle of that, we'd have to rewrite the entire file, right? And that, of course, is too expensive. We cannot rewrite the entire H files every time some user modifies a value. Thus, we had the trick that what happens is that the new values that the users create, or the updated values, they are not stored yet on HDFS. They're just kept in memory. They accumulate in memory. And once the memory is full, we do one flush to one H file of all the key values. So that includes making sure that they are sorted in H blocks with the index and so on and so on. Is everything all right? Oh, yes. Maybe I can just slightly move the screen. As you see, I'm not a light engineer, so okay, now it should be good. Oh yeah, that's quantum. When I'm here, it's not doing that, and when I'm not, yeah, maybe like this. Yeah, maybe better. Thank you. When the memory is full, we flush to an HFile. But then there's the risk, because there's challenge after challenge, right? It was a lot of work to design this for the team. I'm directly telling you the solution, basically. So the other challenge that there was is, while you accumulate the new key values in memory, if there is a crash or a shortage of electricity, everything is gone. So for this reason, we have the write-ahead log, where before we put everything in memory, we log a journal with a journal of all the edits. But the difference is that this log is not sorted by key value, it's sorted by order of arrival. So it's just append operations. So this is why it's no big deal here. The HLog, you just keep appending the new updates, and that's it. And if there is a crash, if there's no crash, we don't need it. But if there is a crash, we have this emergency dump here that we can use in order to restore the data, so we don't lose it. Okay, now we continue. So when we read from HBase, a user is writing some query. It could be a get, it could be a scan, so many ways. And we need to serve the data to the user. How do we do that? Well, we need to think, where is the data? Well, the data could be anywhere. If it's old, it could be in the H files. And if it's new, it could be in memory. So where do we look for the data? Well, the answer is everywhere, right? So we have to look for the depending on what row ID and what columns the user is looking for, we need to look for them in H files. We need to look for them in memory stores. They can be multiple H files, right? Because we might have flushed multiple times. So these are all the key values, and we retrieve everything, and then we give that to the user. Okay, this is how we read. Everybody's following? Okay. Now, here's the thing. After a while, if we keep using the system for days, for weeks, for months, for years, then at some point, we are going to have a lot of H files. So that's going to be very tough and very long in order to query all the H files for data we are looking for. So what do we do? Well, there is another thing that's complementary to flushing that's called compaction, because you can actually merge all of these H files into larger single H files. So you could take all the key values in there and take them, resort them, and then output them back in a single H file. How much time do you think that takes? Is anybody familiar with algorithmic complexity? Yes? Yes, almost, but go ahead, be more specific. Yes? Exactly, so it's exactly like the second part of a merge sort. And because it's only the second part of the merge sort, it's actually going to be linear in the size of the number of keys. What that means is, if we have twice as many keys, it's going to take twice as much time. This is what linear means. And again, you're absolutely right. The reason why it's only linear in the number of key values is simply that it's already sorted in each H files. So what we do is we just traverse all the H files concurrently at the same time, and we merge it. I'm sure you've already sorted card games, right? If you play Yas, who has already sorted a Yas game? Some of you, right? So there's many ways you can do that. But one of the ways is, for example, you split it into, I don't know, 5 heaps, and then you sort each heap, and then you can merge the 5 heaps, right? And when you merge the 5 heaps, it's only, you put them in front of you on the table. You always pick the lowest card amongst the 5 that are on the top of each heap, and you just merge them in that way, right? And the time it takes is just proportional to the number of cards. For whom is that clear? Okay, so this is why it's actually quite efficient. And if we have twice as many key values, then it takes twice as much time. Okay, so this is called compaction. And then you see it's sorted again. It must always be sorted. So now we have, again, an H file that is sorted. So of course, the H file is going to be bigger now, but now it's a single H file. So instead of looking up the data in 3 H files, now we only look up the data in 1 H file, right? So this is the benefit of compaction. So remember, flush and compact. These are the two things we can do. Flush is from memory dumped into an H file, and compact is when we merge several H files into a single bigger H file. Okay. Now, okay, this is maybe more meant for computer scientists, and I don't want to scare you with that, but basically what I want to say here is that these newer technologies like HBase, white column stores, and as we will see also in 2 weeks, MapReduce, they use an approach, the cool name of which is LSM trees, right? So of course, I'm not saying that LSM trees are a buzzword like ChatGPT. Somehow you say GPT, everybody knows what GPT is, but LSM maybe not. But in fact, LSM trees are super important in this. And in fact, LSM trees have to do exactly with what we are discussing now. It's the idea of this flushing and compacting. And it's the idea that we want to be as fast as possible. And instead of storing the data key value by key value, which would take too much time, we just keep copying and scanning through entire H files, right? We flush an entire H file, we merge entire H files, right? This is called batch processing. A batch is an H file, if you want, right? And we just store and write and read the data in huge batches that are called H files, right? And so this is in contrast with the good old ways that we index data in relational databases. That's called the B+ tree. This will cover actually in a few weeks. So this is why I'm not saying much about them, but we'll see them in the context of MongoDB in a few weeks. Okay. So the only thing you should remember here is that LSM trees are the new cool for big data, because this is how we can process huge amounts of data. And now I actually have an animation to show you exactly what this actually means, because the idea is that we store the data first in memory, and then, so that's C0 right there, I'm going to show you. When you start, the new data is in the memory. That's the picture of the memory bar in the machine. Then you flush it, and that's going to go into an H file, right? And this is the level 1. And then you compact it, and that goes into level 2, larger one. And then you compact it again. You might have multiple compactions, right? Then you compact again, that's level 3, and so on, and so on, and so on. All right? Now, who has ever played the game 2048? Wow, many of you, you know that game. Okay, right. So you know how it works, right? You just keep getting these numbers, and then you merge them, and it doubles, right? 1 and 1 becomes 2, 2 and 2 becomes 4, and so on. Okay, well, that's great, because this is exactly what we are going to play here in this visual. So if you understand the 2048 game, then you will understand that. All right. So here it comes. We start with a fresh database, no data at all, completely empty, and the users start using it. And we are looking now at one of the region servers and one of the stores in particular, right? So this is now, the memory is getting full because users are starting to pour data into the database. So now the memory is full. What do? Yes, I heard it. Flush, yes. Okay, so we flush it. So what do we get? Well, we get an H file. And the number of keys is whatever fitted in memory, right? So we flush, we get an H file. That's like the one tile in 2048. Okay, now the memory is full again. Maybe you start guessing where I'm coming at, right? So the memory is full again. So what do? We flush again the H file. Now we have 2 H files of the same size. What do? What is the name? Not loud enough. We merge them, and what is the name of the merge operation? Compaction, exactly. We compact them and get an H file that is twice as big. This is tile 2 of the game 2048. Now we continue. The memory is full again. We flush, get a new H file. Now that's a tile 1. Then the memory is full again. We flush. Now we have 2. So we merge them. That's compaction. Now we have 2 H files of size 2. We have 2 tiles 2 in 2048. So what do? We merge. Now we get a tile 4. right? Then the memory is full again, we flush, we get a 1, then it's full again, we flush, then we compact. Now we have a size, a tile 4 and a tile 2. Then the memory is full again, we flush. Now we have a tile 4, a tile 2, and a tile 1, right? Then it's full again, we flush, and so on and so on and so on, right? For whom is that clear? It's exactly the 2048 game. So this is actually what an LSM tree is, right? And this is the first level 0 is the mem store, level 1 is the mem store corresponding to a tile 1, and then we have HFile of size 2, tile 2, and then HFile of size 4, tile 4. And you can go that way to 2048 and beyond. So what happens is basically, you can also think of it like archaeology, right? When you have millions and millions of years that accumulate, then things start to get stuck at the bottom of the lakes, right? And then there's sedimentation, and then it stays there, right? And then you have the layers that start appearing. So basically, it's a bit like what happens here. That means that all the super fresh and new data is over here. Then the less fresh data is here, and this is older, this is older. And if you actually go deeper and deeper, because when you read data, you need to read from everywhere. And if you go far enough to the left here, you might even find some dinosaur fossils, because that's the super old data, right? So this is how it works, and this is what's called a log structured merge tree. So now I showed it to you with powers of 2, but you can instead, if you don't like 2, you can do it with powers of 3 and beyond, right? That's just the general idea. Okay. So that's, in fact, if there is one thing to remember about HBase and how HBase is actually handling that amount of data, this is it. This is this animation right there. And again, you need to understand that this is batch processing. This is batch processing because we are not manipulating the key values one by one, except in memory. When we are at the level of the H files, we are always reading and writing entire H files at a time. Always entire H files. So this is batch processing. Every H file is a batch of data, and we just deal with the data in batches. All right? That's the secret. That's the secret of HBase. All right. So now there are a few bells and whistles, but of course this is less important, right? So I'm just saying it for completeness that there's a few more things. But again, the one thing to remember is this animation with the 2048 game. Now, what can we optimize? Well, imagine that there are people using HBase and they read old data, but always the same old data. Are you going to read from the H file every time? Because since it's old data is going to be fossilized, right? So it's going to be deeply buried into large H files. So do we need to read these H files every time if it's always the same data access? No, of course not, because what you could do is keep a copy in memory of some of the values in these H files that are accessed a lot, right? But this is called caching, right? The difference with the mem store is that the mem store has fresh data that hasn't been yet fossilized, flushed, but the cache contains copy of already fossilized data. It's already data that is in H files, but it's just a copy in memory because it's super fast to access it that way. So if the user, again, wants the same key values, instead of reading them from H files, we have a copy right there in the cache. Okay. So of course, you don't want to use the cache if the users are also working in batches. If the users are working with specific key values that they ask, then the cache is useful, right? But if the user is running some large-scale analytical query on the entire data that you have on your HBase table, then caching is totally useless because the user is anyway reading everything. So if you read everything, then you can just read it from disk, right? You don't want to bother caching it. And the other one is if the users do not access the data in patterns, meaning that there is a user that might repeatedly access always the same data, then caching is useful. But then there are users that might access data all over the place and always different data. Then caching is totally useless. Right? You might cache things, but you don't need the copy anyway because the user has already gone somewhere else, right? So it will not even request the same key values. So this is then totally useless. Okay. Then there is a second trick. There is a trick because when you have flushed and compacted a lot, you might end up with many H files. still a reasonable number, but it would be nice if we would have a trick that tells us that we don't need to read from all HFiles, that we only need to read from some of them, and we can completely skip some of them. So here I mark 3 as gray, and maybe we have a magic trick that tells us that the keys that we are looking for are surely not in these, right? This is actually done with something called a Bloom filter. In essence, that is a magical device. I'm not going to tell you the detail. It's a magical device that tells you whether or not something is in an HFile. Something a bit more trivial, if you don't want to go into Bloom filters, is just to have a key range. So for example, you could, in addition, in every HFile, you could add at the very beginning of the HFile, the interval of keys that they are in there. This is the minimum key, this is the maximum key. If the key that you're looking for comes before the minimum key, or if the key you're looking for comes after the maximum key, then you agree that you can safely conclude the key is not in there, right? So in that case, you skip completely the HFile. And that saves us a lot of resources because reading from the disk is actually expensive, right? So this is this additional trick that we can skip some of the HFiles, right? And again, Bloom filters is more of the heavyweight version of that. But again, I'm not telling you anything about how these work, okay? Something else, but again, this is almost satellite information. That's not the core. I'm just telling you so that you know. So you have in an HBase database system, you might have plenty of tables. And these tables are stored, they are divided in regions, and the regions are handled by the region servers. But how do you know what region is where? How do you know that? It's like in HDFS, you have the name node that tells you where the blocks are, right? So we need something similar here. How do we know for every region of every table, what is the region server in charge of it? And how are the regions divided? Well, this is done by a special table that's called meta. And that table actually contains all of this information. So there is a table somewhere that has the list of all the tables and all the regions. And for every region, it tells you this machine here is in charge of that region. And this region has the row IDs from this minimum exclusive, minimum inclusive to this maximum exclusive, right? So this is called the meta table, right? So again, if I go back to the architecture, we have this centralized architecture where we have the H master that orchestrates the whole thing. And then we have the region servers that are responsible for the regions. If somebody wants to create, delete, or update a table, it's just like HDFS. They connect to the coordinator node, so the H master. If they are looking for a region, then they can go to, that's kind of an exception, they can go to the region server that's hosting this special table with all the information on the regions. And then once they know which region server to go for, then they go to them, right? And then they can query them, okay? Okay. Now, in terms of API, there is, of course, a REST API, the same REST APIs we covered a few weeks ago. So there is one. There was one for HDFS as well. There is also one for HBase. If you prefer, you can use Java in order to access HBase as well. By then, I actually didn't check if there's Python libraries, or it might be that there's also a way to access it with Python. That's something I could look into. But anyway, yeah, there are many ways of accessing HBase. And of course, there is the shell, right? You can also connect to a shell and do get, put, scan, delete directly writing on the shell. I think you probably have this in the exercises, right? If I correctly remember. We have exercises, yeah. So you'll have an opportunity to do this get, put, scan, delete directly on the shell of HBase. Okay. Now there is something else that I wanted to do. I wanted to now come back to HDFS and attach HBase and HDFS, just to put things a bit in perspective. So for now, what do we know about how HBase and HDFS interact? Well, we know that HBase is using HDFS. We know that the H files and the H logs, these are actually files on HDFS, right? What does it mean? It means that from the perspective of HBase, it's just files, big files. But from the perspective of HDFS, these files are cut into 128 megabyte blocks, because that's what HDFS does. And then HDFS is spreading all of these blocks all over the place on the machines of the cluster, right? But now here's the thing. I want to give you a few insights and hopefully an aha moment. I told you once that the machines that run the HMaster and the name node, this is the same machine. And the machines that run the region server and that run the data nodes, these are the same machines also, right? These are not different machines. So it means that if you look at this here, the HMaster is also the name node, and the region server is also the data node. So what does that mean? Well, it means that if I now look at one of the region servers, which is also a data node, what do I see in there? Well, I see the region server process that is responsible for the regions that it's responsible for, right? So this is what I put on the top. It's a responsibility. But on that same machine, we also have some blocks because it's also a data node, right? So we have HDFS blocks, and these are blocks from whatever files, okay? But now, think again of this flush thing. What happens when there is a flush? Where is the mem store for this region server? Well, the mem store is on that machine, right? We take a region, this is the region server in charge of it, and the mem store is on that machine in the memory of this machine, right? Then we flush everything. What is a flush from the perspective of HDFS? It's a write. We are writing a file, an H file, to HDFS, right? Now, come back 2 weeks ago. What does it mean when we write something from to HDFS? It means we connect to the name node, we ask the name node to write the file, and then we tells us where to put the blocks, right? And then we start putting the blocks there. So we are going to write the blocks, the HDFS blocks of our H file. Do you remember where the first replica of every block is stored in HDFS? Does anybody remember that? We have 3 replicas by default, yes, you know? On the same node as the client. Now, who is the client now? From the HDFS perspective, who is the client? It's HBase. More precisely, the client of HDFS right now is the region server. So the region server is connecting to HDFS, wants to write data, an H file, and where does the first block goes? On the same machine as the region server, which is the client, and thus the same machine as the region server. So that means that when we flush the data to an H file, there is a copy of every block of that H file on the same machine right here, locally. And then there's 2 other copies of the block on other machines, but there is 1 copy of every block in there. This is what I meant with locality. So what does it mean now? If you continue that reasoning, now a user connects to HBase and wants to get or scan keys that are in this region right here that I'm looking at, that this region server is responsible for. Where do I need to read the key values from in order to give the data to the user? Well, you might remember from the HBase lecture that we need to look at the mem store, so in the working memory of this machine, and we need to look at the H files for that region. Now, where is the actual content of the H files, meaning the HDFS blocks? Where are they? On the same machine, because we've just written them to the same machine. So there is a copy of the entire contents of the H file we want to read on exactly the same machine. How fast is it going to be? Quite fast, because it's a local read. We just need to read from the local disk of that machine, right? As opposed to going over the network to another data node, getting the data, right? For whom is that clear? Right now, I'm just pasting together what we've learned in the HDFS lecture and in the HBase lecture. And of course, I'm doing a bit of mind gymnastic, sometimes putting myself in the shoes of HBase, which is a client of HDFS, and sometimes putting myself in the shoes of HDFS, which stores the H files that HBase want to store, right? So the data is all in there. Now, what is going to happen now that we let the system evolve, right? So people use the database, the systems continues to evolve and so on. Well, what happens with HDFS, you might remember, is that the blocks they get spread a little bit over the cluster and so on. And the name node might actually, if some of the nodes are overloaded and some of the nodes are less overloaded, then the name node in HDFS is going to move blocks, right? So if we let the system evolve freely, at some point, this is what's going to happen. Some of the blocks might no longer be on the same machine as they are needed, and they might be somewhere else. It's a bit like, I don't know if they are physicists, but it's like letting a wave function spread, right? So it's a bit of a quantum effect that the blocks start spreading over the network. This is actually bad. Why is it bad? Because now, if we want to access the data for a region that this machine in the middle is responsible for, we are going to need to connect to other data nodes to get the data. This is more expensive because we have to transmit the data over the network as opposed to just reading from the drive of the same machine. But what is going to happen later when we flush and flush and flush? What's going to happen with all these HFiles? They get compacted, right? What does it mean to compact things from the perspective of HDFS? It means we write a new file to HDFS. Do you see where I'm going? Now it's again, because we just wrote a new file, it's again back to the same machine. So this is one of some of the beauty of this engineering is that even though if you would let the H files untouched, at some points the blocks would start spreading all over the cluster, but every time you flush, every time you compact, you magically bring back all the data, all the blocks again to the same machine as a local read, right? Yes? Maybe we can, so that the people on Zoom can hear you. Yeah.
What happens to the two other copies if you merge the one that is on the middle node, for instance?
Oh, so the two other copies are still going to be on other machines.
But alone, not merged.
Yes, you merge them as well, everything. Because again, when you compact, it means that you take existing files. There you go. So you take existing files and you write a new file. So from the perspective of HDFS, you're writing a file. So when you write a file, you create the blocks of the file. So that means that the blocks that belonged to the old H files that are getting deleted, they go away. You get rid of them. And the blocks corresponding to the new H file, the bigger one that you are writing, when you double, like in the 2048 game, these are created. And there is going to be a first copy of the block on the same machine and two other copies somewhere else. Right? Did I answer the question? Awesome. Okay, so again, all I did here, this reasoning, was only deduction. I just logically deducted what's going on based on what we've seen for HBase and based on what we've seen on HDFS. And if you understand this part here, the fact that every time we flush and compact, we get a copy of the blocks on the same machine. And this is absolutely awesome because we love reading from the same machine, right? In fact, there is a name for reading for the same machine. It's called short-circuiting. We kind of can short-circuit HDFS because instead of going through the entire HDFS protocol to the name node and requesting where the blocks are and so on, HBase, which is developed by the same people as HDFS, it's Hadoop, so they cheat and short-circuit the entire HDFS protocol by directly reading locally from the disk without bothering to follow the HDFS protocol. Okay, so that's the short circuit. I think we have the sun that is paying us a visit. So maybe it's coming from here, I think. Let's try this. Maybe that works. Okay. Okay, now we still have time until the break. So I have a bonus part for you. And now you can just sit back and relax because really this is just for the fun of it. Is that, so you remember HDFS was originally the Google file system, GFS, but that's already 20 years old. HBase was originally Google Bigtable, right? So HBase is the open source version of Google's Bigtable. So this is also something like 20 years old. As you can imagine, now things have evolved and Google developed new systems. And so right now, there is something that is a newer generation than GFS and HBase, but it's still the same ideas. It's just that the same ideas are taken to the next level. And so I wanted to show you that next level just because I think it's cool. So I wanted to show you that. So Spanner is basically the HBase, but bigger. Instead of looking at billions and trillions of rows, we are looking at quadrillions of rows. So it's just even larger. So what did they change in the design? Well, they changed a few things. First, they allow the primary key to be over multiple columns, not just the row ID, but multiple columns. In fact, it's just like Cassandra. So when Facebook designed Cassandra, which is also a white column store, they also allow multiple columns. So this is one thing. A second thing is that the timestamp has been promoted to a column. In our case, in HBase, the timestamp is hidden, right? We just hide it in the H files as part of the key, but we do not do it in the table. So here, the timestamp is actually explicitly a column of the table. And then there is something called the tablet that's like multiple regions. So instead of reasoning one region at a time, so a consecutive interval of keys, of row IDs, instead of that, a tablet is multiple intervals of row IDs, right? It's a way of making it scale up. So they call it a tablet. And now, and this is the beauty of it, this is really one, how many of this is, oh, I put 1 trillion in there, right? So probably now you go to quadrillions of rows, trillions of quadrillions of rows. It's absolutely gigantic. As you can imagine, this number is so small. So you remember HBase doesn't fit on a machine. You need a cluster of 1,000 machines. This actually is so big that even a single cluster is not enough anymore, right? So now we need to go beyond just one cluster in the same data center. And so what they have now is a cluster of clusters. This is how you take it to the next level. So now you have still this centralized architecture for each one of the data centers. So maybe, I don't know, there are 5 here clusters. Maybe one of them is in Frankfurt, and another one in Zurich, and another them in Beijing, and another them in New York, and so on, right? So you have all of these clusters. And then you have the universe master that is basically in charge of the entire Spanner thing. So the entire white column store, right? Synchronizing over the clusters. So it means that you have then hundreds, not just of machines, hundreds of data centers, each containing hundreds and thousands of machines, right? So you can imagine, as a university, we would only dream of that because we don't have the money to actually be able to build things like that. But in companies, they can actually do these things. So this is what is actually done. And we are talking about millions of machines on which the data is actually stored. All right. This is where I want to stop this lecture here. I have 5 minutes until the break. So do you have any questions first? Anything that is not clear that you want to ask on Zoom, maybe also? So who is with me on the content? Like, raise your hand. Okay, what we've covered. And on Zoom, please raise your hand too. I'm going to go see the people on Zoom. Raise your hand if you're with us, if the content. I see raised hands. Please raise your hands on Zoom if you're with us. Okay. And any questions on Zoom? Anybody wants to ask anything on the chat? So it means you understand. And otherwise, of course, you can ask us by email, you can ask us on Moodle, and we will be happy to answer your questions. You'll have exercises that you can play with, so there will be an opportunity to use the shell. So you saw in HBase, there is get, put, scan, and delete. So you'll be able to use the shell for that, and of course, you can also use programming languages if you prefer. All right. We have 4 minutes to the break. So I have 2 options. First option is we take the break now. Second option is you still want the break to be on time at 9 and so on. So who wants to take a break now? Oh, we have a majority in the lecture hall. And Zoom, who wants a break now? A few people as well. Okay, so let's take the break now. It is 8:56, so we'll come back No, let me give you the 4 minutes. I'm gonna do the gift to you. So let's come back at 9:15, the usual time, and then we'll start the data models lecture. Thank you very much.